Welcome to today's paper reading. Today's paper is titled, LiveHPS++, Robust and Coherent Motion Capture in Dynamic Free Environment. This paper was published on AR14 by Yiming Ren and colleagues from Shanghai Tech University and the University of Hong Kong. LiDAR-based human motion capture is highly practical in large-scale and unconstrained environments. However, existing methods struggle with noisy data, compromising accuracy and smoothness. To tackle these issues, LiveHPS++ is introduced as an innovative solution using a single LiDAR system. This method includes 3 carefully designed modules that enhance the learning of dynamic and kinematic features, enabling precise motion capture even in open settings. Extensive experiments demonstrate that LiveHPS++ significantly outperforms current state-of-the-art methods, setting a new benchmark in the field. Figure 1 provides a detailed visualization of the motion capture performance of LiveHPS++ in a real-time captured scenario characterized by complex human-object interactions. On the left, reference images are displayed to contextualize the scene. The middle section of the figure contrasts the noise point clouds at the top with the corresponding mesh MAO results at the bottom, showcasing the effectiveness of LiveHPS++ in handling noisy data. For a clearer demonstration, the right side of the figure zooms in on specific cases, with point clouds depicted in white, highlighting the method's ability to distinguish and process detailed motion data even under challenging conditions. LiveHPS++ is an innovative approach for capturing precise and coherent human motions in vast, unregulated environments using a single LiDAR system. The method consists of 3 specially designed modules: the trajectory-guided body tracker, the noise-insensitive velocity predictor, and the kinematic-aware pose optimizer. These modules work together to enhance the robustness and accuracy of motion capture, particularly in complex scenarios with noise and occlusions. Extensive experiments demonstrate that LiveHPS++ significantly outperforms existing methods, achieving state-of-the-art performance on various datasets. The evolution of motion capture technology has seen significant advancements from optical-based systems to more recently DR-based methods. Optical-based motion capture initially relied on camera-tracked markers, but has since evolved to include markerless technologies that use multi-view algorithms. These methods, however, face challenges with multi-camera synchronization and calibration. Inertial-based motion capture offers advantages such as being resistant to occlusions and unaffected by lighting conditions, but typically requires performers to wear intrusive suits with multiple IMUs, leading to issues with drift errors over time. LiDAR-based motion capture, known for its precise depth sensing, is robust across various environments but faces challenges with noise and data sparsity, particularly in outdoor settings. Figure 2 illustrates the comprehensive pipeline of LiveHPS++, a robust and coherent motion capture system designed for dynamic free environments using a single LiDAR system. The pipeline is divided into 3 primary modules: the trajectory-guided body tracker, which predicts human joint and translation by capturing dynamic characteristics through trajectories; the noise-insensitive velocity predictor, which employs a cross-attention mechanism to enhance features and regress joint velocities, minimizing noise impact; and the kinematic-aware pose optimizer, which refines the accuracy and coherence of motion capture results using predicted velocities. The final stage involves the SMPL solver, which regresses the parameters of human poses and shape. The detailed network structure of each module is also depicted, showcasing the sophisticated system implemented to achieve precise and coherent human motion capture in complex, noisy environments. The LiveHPS++ methodology is structured around 3 critical components designed to enhance the robustness and coherence of human motion estimation in dynamic environments. The first component is the trajectory-guided body tracker, which predicts human joints and translations using global dynamic information. This is followed by the noise-insensitive velocity predictor, which leverages the association between human joints and the original point cloud to regress joint velocities, aiming to optimize results and mitigate noise impacts. Finally, the kinematic-aware pose optimizer enhances the coherence and accuracy of human motion by using the predicted velocities. The methodology takes sequential noisy point clouds as input and aims to output sequential SMPL parameters, including human poses, shapes, and translations. Figure 3 illustrates the process of normalizing point clouds. The light green point signifies the human root positions, and the dark green point marks the origin of the coordinate axis post-normalization. On the left, the sequential point cloud without noise shows a stable data distribution after normalization. Conversely, the data on the right, affected by noise, exhibits a more erratic distribution post-normalization. Figure 4 illustrates the noise-motion dataset simulation pipeline, which integrates dynamic human motion and static object noise to simulate real-world human-object interactions. The pipeline categorizes noisy objects as either dynamic or static. Dynamic objects can appear unexpectedly and significantly alter the point cloud distribution, while static objects introduce noise through human-object interaction or proximity. To further diversify the noise types and their distribution, the pipeline employs data augmentation techniques like random rotation and scaling. This approach is critical for accurately reflecting real-world complexities and significantly boosting the network's generalization capability. The noise-motion dataset is designed to address the limitations of existing synthetic datasets used in LiDAR-based methods. It leverages human motion data from surreal and 3D object models from ShapeNet to simulate complex noise patterns resulting from human-object interactions. This approach significantly enhances the network's generalization capability by accurately reflecting real-world complexities. The dataset categorizes noisy objects as either dynamic or static, with dynamic objects appearing unexpectedly and altering point cloud distribution, while static objects introduce noise through interactions or proximity. To further diversify noise types and their distribution, data augmentation techniques such as random rotation and scaling are employed. Compared to the FreeMotion OBJ dataset, noise-motion offers a richer collection, including 51,300 unique 3D object models and 1,021,802 human motions, highlighting its importance for advancing LiDAR-based applications. In this section, we present comprehensive experiments to validate the effectiveness, robustness, and coherence of our method, LiveHPS++. We compare LiveHPS++ against state-of-the-art methods including LiDAR-CAP, LIP, and LiveHPS using metrics such as J/V error, angular error, and acceleration error. Additionally, we conduct ablation studies to assess the contribution of our network architecture's components, focusing on the trajectory-guided body tracker, TBT, noise-insensitive velocity predictor, NVP, and kinematic-aware pose optimizer, KPO. These studies highlight the critical role of each module in enhancing both accuracy and coherence of human motion capture in noisy environments. Figure 5 presents qualitative comparisons of motion capture methods, highlighting the superior accuracy of point cloud matches in estimating pose, shape, and translation. Each point in the coherence evaluation visualization represents the frame-wise global human translations observed from a bird's-eye view, emphasizing the method's ability to maintain coherence and precision under various conditions. Figure 6 presents an ablation study focusing on the selection of the temporal window size within the kinematic-aware pose optimizer, KPO, module and the impact of the noise-motion data volume on model performance. The study reveals that a temporal window size of 32 yields the best results, leading to a decrease in vertex error, VR, and a more pronounced reduction in jitter, indicating more accurate and coherent sequences. Additionally, the study demonstrates that increasing the volume of noise-motion data from 0% to 100% improves network performance, highlighting the significance of synthetic data for enhancing generalization in noisy conditions. Table 1 provides a comprehensive comparison of our method, LiveHPS++, with state-of-the-art methods across various datasets. The metrics evaluated include acceleration error, accel error, jitter, joint/vertex error in position and scale, J/V error, PS, and angular error, on error. Lower values in these metrics signify better performance. Notably, LiveHPS* operator, which is trained on a combination of real and previously cleaned synthetic data, serves as a benchmark. The table highlights the superior performance of LiveHPS++ in handling dynamic motion coherence, especially in environments with severe noise, as evidenced by its lower accel error and jitter values compared to other methods. This underscores the robustness and generalization capabilities of our approach. Table 2 presents the results of ablation studies conducted on our network modules using the FreeMotion OBJ dataset. The study evaluates the internal details of each module, highlighting the critical role of the trajectory-guided body tracker, TBT, in enhancing accuracy within noisy environments and the effectiveness of the kinematic aware pose optimizer, KPO, in optimizing the coherence of sequential motions and translations. Additionally, the table demonstrates that our translation estimation method significantly outperforms those proposed in LiP and LiveHPS, showcasing our method's advanced capability in capturing precise and fluid human motion translations. In this paper, the authors introduce a novel single LiDAR-based approach that excels in capturing precise and coherent 3D human motions across various unconstrained environments. By leveraging dynamic and kinematic attributes from global human movements, the method effectively mitigates significant noise. Additionally, a new synthesized motion dataset is presented to enhance the network's adaptability in noisy conditions. Comprehensive experiments show the superiority of this method, particularly in local pose accuracy and global pose coherence, making it highly suitable for practical applications. Thank you for watching.